Today we're going to begin covering Chapter 6, Covalent Compounds. We're going to look at how electrons form covalent compounds and what some general properties of those compounds are. To begin with, let's do a quick review. We talked last chapter about ionic compounds and ionic bonding. We know that the electrons are the particles involved in covalent or in ionic bonding. We know that one electron is transferred in an ionic bond. So we end up with a positive ion and a negative ion, and those two will attract each other. And again, if you take a look at this, a sodium ion and a chlorine is in the atoms. One electron gets transferred or kind of stolen by chlorine, and we end up with Cl- and Na+, which in turn attract each other and form a bond. A covalent bond happens when you don't have the electron completely transferred. We have something called sharing the electrons. And those shared electrons will actually move around both atoms at the same time. You can see the electrons in this orbital right here. They're orbiting both nucleus at the same time. This whole cloud is all electrons. How is that working? Well, we have the nucleus of each atom is attracting the other electrons. It's attracting that electron and that electron. This other nucleus is attracting this electron and that electron. And together that makes it more stable. Now there are forces of repulsion. Again, the electrons don't want to be near each other. The nucleus don't want to be near each other, which is why we still see that they are spread out. They're not touching, but we have these electrons going around both of them. Now energy is released. We said any system that becomes more stable is going to a lower energy state. So we'll see that energy is released. And this graph is actually showing you if this is energy on the y-axis and distance is on the x. As these electrons get closer, they go down in energy. And as they get even closer, they drop even lower in energy, until we have what we call the potential energy or the bond energy to create this covalent bond. It's the energy given off. So how close will they get? Can they eventually close on top of each other? No, they can't, because we have repulsive forces between the nucleus of one and the nucleus of the other, and also the electrons. At some point, that repulsion becomes high enough that the attractive forces has stopped, and they will stop. So we can measure how close they actually get in something called the bond length. If we look at two hydrogen atoms and we actually begin to take this one and pull it closer to the other one, it's not going to completely touch. How close will it get? Well, we're able to actually measure the nuclei of these atoms, and we can tell approximately how close. And they're not going to, again, get this close and just stop. We'll see them kind of vibrating around as the electrons are floating around both of them, and you'll see an average bond length of 75 picometers. And this is just for the hydrogen. This is just an example of the H2 molecule. Energy is required to break that bond. Once you've formed a bond, you gave off energy. Remember, we also have the potential energy drop. So if I want to break those back into individual atoms, I have to put this energy in. The closer the bonds, the shorter the bond length, the higher the bond energy. They're closer, they've dropped to a lower bond potential, and you need more energy to break it then. Now, one way scientists wanted to find out, can we start to categorize these bonds? Can we figure out how these electrons are shared? Do all atoms share equally? And the answer is no, they don't all share equally. If you remember in our periodic table, last chapter, or back in chapter 4, we talked about something called electronegativity, which is the ability of an atom in a compound to attract an electron. So Linnaeus Pauling just randomly assigned fluorine as a 4.0. Fluorine is the highest electronegativity anything can have. And if you looked at the periodic table, we would see it increasing as you go across. So this is the periodic table. So the highest place is over here. Okay, with this fluorine being the highest. Everything else is measured relative to fluorine. And this is a table which just shows, and I'll give you a handout in class tomorrow, showing you just some electronegativities. Again, fluorine is up here at 4, and you can see increasing. Over here they have very low electronegativities. They don't have a lot of attraction in a compound for those electrons. They're more likely to lose the electrons. That's why when we form ionic bonds, they lose electrons. They don't have a great attraction for them. This side of the table with your nonmetals tend to attract electrons. So electronegativity helps us predict what kind of bond is going to form. We actually can calculate the difference between those bonds, between the electronegativity for those two different atoms to figure out what kind of bond. And we're going to name 3 different types of bonds we're going to talk about. The first is nonpolar, which is an equal sharing. So nonpolar, it does not have poles. If you think pole is being opposite, there's no opposites involved. It's completely shared. Ionic is what we talked about in the last chapter, where we actually have a transfer. And polar is what we're going to find very interesting in this chapter. So we're talking about polar bonds. This is when things are unequally shared. Maybe one electron is a little bit stronger, but can't quite take it all away. Think about a tug of war with 2 teams who are almost equal, but not quite. They're going to pull to one side, but they can't quite get the other team off their feet. And these are differences between 0.5 and 1.7. We'll classify those as polar. Your book says something like 2.1 here. Use this number of 1.7. It is more correct if you look at any other literature besides your book. So use the 1.7. And again, change this in your book. It should be 1.7, not 2.1. Again, we look at the distribution of our electrons. In a nonpolar, we see that these are very evenly distributed. Electrons are going around both of them at the same amount of time. An unequal or polar means that we have more electrons over here. There's some electrons here, but there's not as many. The electrons spend more time on this side because it's a larger side. And if there's more electrons there, we see a charge. Now if you notice, this is kind of a weird sign. It's not a negative charge because it's not a full negative. It's a partial charge. Partial negative or partial positive is the way we write that. Kind of like a weird, almost not quite closed 8. But that's a sign that stands for partial. And it just means that the electrons have not completely transferred. This would be an ionic compound if they have completely transferred. And we'll use electronegativities tomorrow and begin to predict bond types. And we're going to do this in class and see which you can figure out from there. Alright? Signing off for now, this is Mrs. Schroeder.